do that as we test our chat features to see if you guys are comfortable and know what you need to do. Please post in the chat which topic in chemistry do you find the most challenging and which topic in chemistry do you find the easiest. Post that in the chat. So just write hardest, this one, or rather not hardest, most challenging, this topic, and then the easiest topic, this topic in that case there. Post that so long. I'm going to get my screen shared, and then we're going to pick up today's lesson. We're going to start with question 5, which is rates of reaction, and hopefully we're going to have a good time today. After that, we're going to cover some chemical equilibrium. There's some acids and bases, as well as electrochemistry questions coming up. Awesome, guys. Just give me 2 minutes for my screen share, and I'll be with you just now. Okay, there we go. Taffy or Theo, please confirm if you guys can see my screen.
Can see it, Ernest.
Okay, perfect. Thank you so much. So let's have a quick look at this question together, and then let's try and break it down, right? So as we do this question, let's quickly jump straight in. Okay, let me quickly have a look at some of the responses in our chats. Okay, most challenging, there's acids and bases. We've got Mr. Bless Ratau on the live. Top of the evening, Mr. Ratau. Mr. Ratau was one of our team members. Shout out to you, Blessing. Just giving a shout out there. And then the imposter is most challenging acids and bases. Let's see. Khalalelo says chemical equilibrium. Tsegofato says acids and bases. Bunatseho says acids and bases. Mutlalipula says chemical equilibrium. Premier says acids and bases a little challenging. Organic chemistry and chemical equilibrium, very simple. Love it, guys. Love it, love it. Thank you so much. I can see there's a lot of acids and bases challenges in this case here. Don't worry, we'll take our time. I could pick it up in the lesson on Tuesday, that it was a bit of a problem, but we'll take our time with it today. I'll try and give a bit more time. So I pushed on Tuesday so that we've got more time in today's lesson. No no multiple choice. We'll just jump into the questions straight. Okay. So my screen is up. Let's jump straight into these questions, right? So we're going to start off with question 5 and pick it up from there. Thank you so much for all the ones that are engaging. If you haven't engaged, don't be shy. Jump straight in and get active. All right. So looking at this now, we've got question 5 says, the reaction, apologies, I'm going to just stop my video just for the guys on Zoom. If it helps you save a little bit of data, it goes a long way. Then I'll put my video on right at the end again so you can see my face. But for now, it's not about my ugly face. It's about the content we're about to do. All right, question 5. It says the reaction of zinc and excess dilute hydrochloric acid is used to investigate factors that affect reaction rate. The balanced equation for the reaction is zinc plus hydrochloric acid, giving us zinc chloride and hydrogen gas. The reaction conditions used and the results obtained for each experiment are summarized in the table below. The same mass of zinc is used in all the experiments. The zinc is completely covered in all the reactions. The reaction time is the time it takes the reaction to be completed, right? One of the things I want to always, again, do is highlight some of the key things in this case here, right? Let me just get a slightly smaller highlighter. This excess hydrochloric acid is quite important, right? And the reason why that's important is because it tells us that in terms of the volume of hydrochloric acid, we have got all that we need. The limiting reagent in this case is going to be our zinc. So the volume of our HCl is not really going to affect the rate of our reaction or even the extent of our reaction in terms of the yield, right? Because it's in excess. The limiting reagent in this case is going to be our zinc. All right. Now we can see experiment 1 up until 5, we're given the following parameters: the concentration of our acid, the volume of our acid, the state of division of our zinc, as well as the temperature of our acid and the reaction time in minutes. 5.1 says, experiment 1 and experiment 5 are compared. Write down the independent variable between experiment 1 and experiment 5. This is that moment where you guys need to get active, right? You guys are going to post in the chat there, what would the independent variable be for between experiment 1 and experiment 5 when they are compared? What would the independent variable be? Success with the quick fingers there. right? Thank you for your answer in that case there. While everyone else is typing their answers, I'll quickly remind you guys again. Remember, you're going to have your independent variable, dependent variable, control variable, right? The independent variable is the one that you are going to manipulate. The dependent variable is the one that depends on your independent. It's the one you're going to measure. And then your control variable is the one that you will keep the same, right? Thank you, Dimpo, as well, for quick fingers there. All right. And then Alpheus, Khalalelo, thank you guys for your answers. And Didi, you guys are all right. Temperature will be that one, right? Because if you look at the reactions, let's quickly have a look. We've got a concentration that's exactly the same. We've got a volume that's exactly the same, right? Our state of division is exactly the same. The key difference there is going to become our temperature. So that difference is what we are going to manipulate to see what the outcome will be. And that outcome will be our reaction time, the dependent variable. So the answer we have for 5.1 there, our independent variable is going to be temperature. If you got that right, give yourselves a round of applause. If you didn't answer, come on. Next time you can get active, you can get engaged with us. Let's see how we can do going forward. 5.2 is going to be as follows, right? So 5.2 says define a reaction rate. Definitions count for a lot of marks in your paper, guys. Please don't underestimate how many marks you can grab with definitions. Definitions count for a lot of marks. So let's define our reaction rate. And you can, there's a number of definitions when it comes down to this. All right, Bongani says you got it now. Well done, Bongani. Shout out to you, man. Okay. So in terms of reaction rate, there's a number of definitions you can give, right? It's the change in concentration of your products or reactants per unit time. Another way you can put it is the change in the amount or the number of moles or the volume or the mass of your products or reactants per unit time. All right, you can also say it's the amount or the number of moles, the volume or the mass of products that are formed, or the reactants that are used up per unit time. Or another one you can give is to say it's the rate of change of concentration or the amount or the number of moles or the volume or the mass, right, of your reactants and your products in that case there. Thank you, Success, the change in the concentration of either reactants or products. Success, please note, you made a little bit of a mistake there. And this definition question is tricky because you don't get 0, 1, or 2. You either get all the marks 2 or you get 0. And what you didn't mention there is per unit time. That's very important. When we talk about rate, whenever you get this word here, rate, the first thing that must pop into your mind is delta T. It's something over delta T. And if you don't mention per unit time or you don't mention the rate of change, you end up losing marks. So Success, please note there, like I told you guys on Tuesday, don't give the examiner a single chance to mark you guys down. You must make sure that you nail all those marks. So I'll quickly write down the definition that I generally tend to choose. So it's going to be the change in concentration of our reactants or even our products per unit time. Awesome, guys. I hope that makes sense. Please remember, if anything doesn't make sense as the lesson is going, don't wait until the end, until you're completely lost. Ask the questions as we go so that you make sure that you're with me the whole time. All right. Okay. 5.3, write down the value of X in experiment 4. Let's quickly go back. I'm going to show the table to you guys, and I want you guys in the chat to go look at how can we determine the value of X. So what would the value of X be? I'll give you guys 2 minutes to think about it. So X is basically what they're asking for is the reaction time of reaction 4. Now, how would you guys find the reaction time of reaction 4? Once you've got it, pop it in the chat, and then I'll give you guys a little bit of a chance, and then we'll do the solution together. Thank you, Haibo, with the quick fingers. And thank you for following as well. Thank you, Ntombela, for following. Really appreciate it. Right. Stababa as well. Thank you for following. Really appreciate it. Success. Thank you for the quick fingers there. You're awesome. And Garabo, thanks for following. Okay, Team TikTok is beating Team Zoom today in terms of interaction. So come on, Team Zoom, we got to get our interaction up, right? The more you interact, the more you put your answers in there. What happens is that, guys, please also remember, right? Don't be scared of being wrong. Being wrong is good. Being wrong is how you learn. So if you had a misconception and you keep it inside, you're not going to fix it and you're not going to be able to change that misconception. So be brave. No one can see your face. Put the answer in. Because if it's wrong, I'll get to correct exactly why your thinking might be misguided in any way. And the worst part is, I'm going to give you the right answer. That's the worst case scenario. You leave here with the right answer. Success is asking if they can join via Zoom. Success, you're more than welcome. Go to the learning space that's here today. Click on live class and it'll let you join via Zoom. Go for it. Okay, let's have a look, right? So let's look at this one. So we were asked to find the value of X, the reaction time for experiment 4. Now, when we look at experiment 4, we need to look at all the different values. So let's quickly compare them, right? Experiment 4, we need to find another experiment that's quite similar to it, right? So already when I look at the concentration, experiment 2 has the same concentration. The volume is different, but that's not a problem. Remember what I mentioned earlier on. We were told that the hydrochloric acid was in excess. It being in excess means it's not the limiting reagent. So the volume of a hydrochloric acid is not going to affect our rate of reaction. So that basically might as well be the same thing for all intents and purposes, because in reaction 2 and 4, the amount of hydrochloric acid that reacts is going to be identical. State of division, granules and granules. Temperature of HCl, 25 and 25, which means the reaction times have to also be equal, which then we can see in this case that X must also be 14. Hope that makes sense, guys. Let's quickly go put that answer in there. That's going to be, let's check the units, minutes, right? So it's going to be 14 minutes in that case there. All right. Hope that makes sense, guys. If it doesn't, please, just post in the chat to repeat or put a hand up and I'll quickly go through it. All right. I will even say because the volume of HCl won't affect the reaction time since it's in excess. Exactly, right? Well done. Success says they still don't understand. Not a problem, Success. I'll quickly repeat, and Twilight says repeat. I'll definitely repeat for you guys, right? So let's go back up here. So when we're up here, we have to come and now compare the different reactions. We don't know what the reaction time originally for this thing was, right? Let me quickly erase this stuff. So we don't know what the reaction time originally was. So we need to try and find a reaction that's very similar to reaction 4 and try and see where we can find similarities. So in that, I said, well, with reaction 2 and 4, they have the same concentration of HCl. Let me skip the volume for now. They have the same state of division of the zinc. They have the same temperature. So these reactions are very, very similar. The only thing that seems to be different is that the volume of my acid is different. But now I'm saying, actually, wait, that shouldn't matter, right? When you think about stoichiometry in grade 11, you guys go and you learn about limiting reagents, right? Limiting reagents are the things that basically allow your reaction to go as far as they can, right? You can't make more products than you've got your limiting reagent. Now, in this reaction here, our limiting reagent is not the hydrochloric acid, it's the zinc. So the zinc is what determines how much I'm going to make. Also, because remember now in this case here, the volume of your HCl does not affect your rate of reaction anyway, right? The volume does not affect your rate of reaction. What will affect the rate of reaction is the concentration. That's important. So the volume doesn't affect the rate of reaction. And even when I think about now the extent of my reaction, basically how many products I will produce, the volume will only be effective if it was the limiting reagent. But in my hydrochloric acid, the volume is not my limiting reagent, meaning it doesn't matter how much, because when I have this reaction take place, I'm going to use less than 200 cubic centimeters of HCl. So even if I've got 400, doesn't matter. It won't affect the reaction results in this particular case. So as a result, these two reactions are, for all intents and purposes, identical, which means in this case there, my reaction times should also be the same. And that's why I now know that the reaction time for reaction 4 should also be 14 minutes. Hope that makes sense. If it doesn't make too much sense, please note we're going to be recording the session, and then you can quickly go back and watch it back, listen to it, go look at your notes, right? What you can also do is you can go to our YouTube, watch our video on rate of reaction, where we take our time going through the topic. Watch our video on rate of reaction. That might also help you make sense of this question. It's quite a pleasure success. Okay, and then someone asked there, do we have to do any calculations, or do we just compare between the experiments? So in this case, for this particular question, where they were asking us for that unknown value X, we didn't need to do any calculations. Sometimes if they ask you for the rate of a particular reaction, you can go calculate how many moles were produced over how many seconds or minutes, and then calculate the rate of reaction. For this question, no calculation was needed. All we had to do was compare and find a similar example, because we don't really know what time it was produced in. So we can't really easily have a calculation for this question. Okay, hope that makes sense to you guys. Let's jump on to the next question. So we've got the question 5.4, right? And our 5.4 is going to be as follows. It says the Maxwell-Boltzmann energy distribution curves for particles in each experiments 1, 3, and 5 are shown. So we can see there's A, there's B, there's C. And then they showed us our activation energy. Then it says, identify the graph A, B, or C that represents the following. They want the graph that will represent experiment 3, right? Experiment 3, let's quickly have a look at what is the key different figure in experiment 3 compared to the other experiments. So as we look at this, experiment 3, you can tell its main thing here, it's got a much higher concentration of our acid than everything else. That's its one bigger thing. Now, when we think about the Maxwell-Boltzmann distribution curves, right, there's different ways our curve can be affected. Let me quickly try and add a page here so you guys can quickly see. So remember, when we do our Maxwell-Boltzmann distribution curve, usually what you'll find is you're going to have your graph, okay, like this, and then you'll have a baseline curve that looks like this. Now, with our baseline curve, there's several things that can happen, right? If we increase the concentration, right, then what's going to happen is that this is going to happen, right, by increasing our concentration. If we increase our temperature, for example, so in this case here, this is going to be concentration 2 greater than concentration 1, right? Everything's going to go up in our Maxwell distribution curve if we increase concentration. If we increase temperature, however, this is going to happen, right? That's temperature 2, which is greater than temperature 1. So we need to find, okay, experiment 3 has a much higher, we saw concentration, right, than the other experiments. So how do we expect the curve to be changed? We expect the curve to be slightly greater, taller than all the other curves. And then when we come back and look at, well, which curve is going to be taller here? Very clearly, curve B is taller than all the other curves. So that's how we know that then experiment 3 is going to be the answer. That's 5.4.1. We know our answer is going to be curve B, right? And why is that? Because it has the highest acid concentration, right? It has the highest concentration of HCl, right? Which means it'll have more particles, it has more number of moles within its reaction. So that's the key thing. Twilight got the right answer there in the chat. Well done to you, Twilight. And also Tebello got the right answer. Well done to you guys there. Okay, let's look at the next one quickly. The next one's going to be experiment 5, which is the curve for experiment 5. So let's go back and let's see what is the key difference with experiment 5. So experiment 5, we can see here, the concentration, it's got similarities with the other ones. The volume has similarities with the other ones. The state of division has there's other powders as well, right? The temperature, there we can see 35. It's the highest temperature reaction out of all of them there. Right? So experiment 5 has got the highest temperature. Let's look at what we expect to see. Remember, I showed you in this purple one here that when we see temperature, the graph is going to be flattened and shifted to the right, meaning more particles have more energy, right? In that case there. Twilight jumped in the chat there with answer C. And when we come back and look, it is indeed C, right? The one that's sort of shifted to the right, flatter than all the other ones, will have the highest temperature. All right, well done to you, Twilight. Let's quickly put our answer there. And then we have to give a reason for our answer. So the answer is going to be C. The reason is it has the highest temperature of all the other ones in that case there. Okay. Hope that makes sense to everyone. Thank you as well there. Butumelo, Tebello, Alpheus, Kalalelo, you guys all got the same answer as well. Really, you guys are awesome, man. Okay, thank you to Fundo and Anita for following us. Really appreciate you guys, man. Okay, let's jump on to the next question. So the next question is going to be 5.5. Now, 5.5 says experiment 6 is now conducted using a catalyst and the same reaction conditions for experiment 1. Let's quickly go back and look at experiment 1. So experiment 1, concentration of 2, volume of 200. It's going to be zinc in powder, temperature of 25, and the reaction time is 7 minutes. Okay. But the only difference is that they've added a catalyst, meaning nothing else is going to change. The only thing that'll change is our reaction time will go down, right? Because our catalyst speeds up a reaction, right? Which is very important. Okay. So then we're going to get asked the question, 5.5.1, what is the function of the catalyst in this experiment, right? So in this experiment and any other experiment, right, the function of a catalyst is, there we go, people are already given the, provides the alternative pathway, lowers the activation energy, speeds up a chemical reaction, lowers the activation energy. Well done, guys. Thanks, Karabo. Thanks to Umpumetu, Debello, Kalalelo as well, and Twilight, right? So in this case here, we can put any of those answers in that case there. We can say it speeds up the reaction, it increases our reaction rate, provides an alternative pathway, lowers the net activation energy. Any of those answers will do. So in this case here, we'll just say it'll speed up the reaction. And remember, it speeds up our reaction without taking part. But in the definition, they don't need you to state that part. You'll get the mark without stating it. But it's important to note that it doesn't actually take part in the reaction. It doesn't undergo chemical change. Or you can say lowers activation energy. Thank you, Dinani, for that as well. So I'll put up all the possible answers. So it speeds up our reaction. You can also say increases the reaction rate. It increases our reaction rate. You can also say that it provides an alternative pathway. Right? It lowers the activation energy. Any one of those answers will do, guys. Okay. Thank you for the guys who are engaging. Really appreciate you guys, man. Okay. Hey, Theo, what's up?
There's a question in the chat, huh? I don't know if you can see it.
Oh, from Alpheus. Thank you so much for bringing that to my attention, Theo. So what about a catalyst? How would the Maxwell-Boltzmann distribution curve behave when a catalyst is added? That's a great question, Alpheus. So the catalyst would not change our curve, right? What would happen is that, so let's say for this reaction here, right? Our activation energy, so remember with this, now here, it's going to be basically on the left-hand side of our curve, right? You're going to have your number of molecules. On the right-hand side there, you've got your kinetic energy. And then we've been given the activation energy is a point on my y-axis, right? It's a particular x value that says at this point is our activation energy, whatever that activation energy is. So remember with the definition of catalyst, what does it do? It lowers my activation energy. So when you add a catalyst, all that's going to happen, sorry, let me do this. All that's going to happen is I'm going to do this. And then I've got now a new activation energy. And in this case here, activation energy 2, which is the one I drew, is less than activation energy 1, the one that they gave us originally. That's what happens to our Maxwell-Boltzmann distribution. Thanks for the question, Alpheus. It's a really good one. Okay. Let's jump through. Now, 5.5.2 says, how will the heat of reaction in experiment 6 compare to that of experiment 1? Choose from greater than, equal to, or less than. In this case, I don't even have to go back to my table to see, right? Because they try to think about a number of things, but let's look at what they're actually asking us, the heat of reaction, right? Heat of reaction is what? It's going to be my enthalpy, my delta H. But now when I think about delta H is based on what is the energy of my reactants versus energy of my products, right? When I add a catalyst doesn't change the energy of my reactants. It doesn't change the energy of my products, right? All it does, it changes my activation energy, not my heat of reaction. Let's draw it here and have a quick look. So if I were to come and look at our energy profile for this reaction. So our energy profile would look like this, right? So we would have, for example, I can't remember whether this is an exothermic or endothermic reaction. Let me quickly go back and check. They didn't specify, but it's an acid that's with a metal. It's going to be pretty, what's this, exothermic anyway. So let's quickly come back and draw that. So that'll probably be an exothermic reaction, right? And if it's not, I apologize, but the point will still make sense. So we'll have energy of our reactants, we'll go up to our activation energy, and then energy of our products. So that's what we're going to have there, right? So this is going to be energy of our products. I'll call that EP. This is going to be energy of our reactants. I'll call that ER. When we think about our activation energy is this energy here, right? The difference between my energy of the reactants and what we call our activated complex up here, right? Quickly write that in slightly smaller. Okay, this here, which is our activated complex. So our delta, our activation energy, EA, right? That's going to be at that point there, activation energy. But what our delta H is not that. Our delta H is going to be here. The difference between my energy of the reactants and energy of my products. So when I add a catalyst, how does that change my reaction? Adding a catalyst is simply going to do this to my reaction. It's going to bring my activation energy down. Let me remove this. Let me just move this out. Yeah, to there. At least then you can see it there. Okay. Now, if I add a catalyst, what's going to happen is that my curve is simply going to do, sorry about that. This. It'll start at the same place and it'll end at the same place. What's going to change is my activation energy will be made less, right? So I'll just lower my activation energy, but my heat of reaction doesn't change because I'm not changing the energy of my products. I'm not changing the energy of my reactants. So in this case here, the answer for that question is going to be that the heat of reaction is going to be equal to the heat of reaction for my previous reaction. Nothing will change here. Hope that makes sense to you guys. I can see the Alpheus Naledi, Motlalepule, Vuisile, Justine, Premier, Katlejo. A lot of you guys got the right answer. Well done to you guys there. Okay, Team Zoom has woken up now. They're engaging, they're beating Team TikTok. So Team TikTok, you gotta pull your socks up. All right, let's go to the next question. Okay, the last question for question 5.6 says, calculate the average rate of reaction in moles per minute with respect to zinc for the experiment 2 if 1.5 grams of zinc are used, right? Okay, so if 1.5 grams of zinc are used, what is going to be our rate of reaction? So remember, our rate of reaction, we need to look at the change in moles over change in time. So to do that, we must first figure out, well, how many moles of zinc were used? And zinc is good to use in this case because remember we said at the beginning. Hey, Theo.
Sorry to disturb you. There's a hand from Relebohida.
Okay, Relebohile, if you can help her unmute, then she can speak. Relebohile, please remember academic questions only, right? Lebukile, you can speak, you can unmute.
Okay, sir, can you please repeat the previous question?
Which one? 5.5.2.
Yeah.
Sorry, Lebukile, your connection's a bit off. 5.5.2. Is that the question I need to repeat? If it is, please post in the chat or give me a thumbs up. Okay, I'll quickly repeat it anyway in the case that that's what you were asking for, and I'll quickly go through it. So the question's asking, how will the heat of reaction in experiment 6 compare to that in experiment 1? Choose from greater than, equal to, or less than. So what I'm saying right now is when we look at our energy profile for the reaction, right? Heat of reaction is simply going to be the difference in energy of my reactants and energy of my products. All a catalyst does, it lowers my activation energy. So what my catalyst does, it changes my activation energy from that to this one here, right? It makes my activation energy less, but it doesn't change the energy of my reactants. It also doesn't change the energy of my products. Meaning, if this is the same and that is the same, the difference, which is my delta H, will remain the same through all the experiments, 1 right up to 5, right? So in this case there, they're asking specifically about experiment 1 and experiment 6. Then in that case, it's going to be equal to, because the catalyst changes my activation energy, not my heat of reaction. And which means it doesn't change your energy of reactants, energy of your products either. So it will remain equal to. Okay, so someone on TikTok said that they're lost. If you were lost with regards to that question, I just repeated it. If you're lost with regards to the whole topic, please go watch our video on rates of reaction. It'll help you catch up. And then once you've caught up on that topic, you can come back to this. The recording of this session should be up in a couple of days. And then you can watch the recording of this session. And then hopefully you'll be able to pick up on that one. Awesome, guys. All right. Now, the last question for question 5, calculate the average rate of reaction in moles per minute with respect to zinc if experiment 2, of experiment 2, if 1.5 grams of zinc was used. Remember, for our rate of reaction, we need to be looking at the change in concentration or change in number of moles or whatever it is. In this case here, they specifically said in moles per minute. So what is the change in the amount, right? So let's first find the number of moles of zinc that we used up. So what did we use up? Let's find that. The number of moles of zinc that we used up. We got mass, so we're going to use mass over relative molecular mass. Our mass is given to us in grams as 1.5. And then the relative molecular mass of zinc is 65. And then if you put that into your calculator, you should get a value of 0.023, right? So that's what we have there. And now we need to think about what was the change in moles over change in time, right? So in this case here, our rate is going to be our change in moles divided by our change in time. Our change in moles is final minus initial, right? So final, we assume the zinc was used up completely because it was our limiting reagent. So final is going to be 0. Initial is going to be what we worked out now, 0.023. And our change in time, they said, what is our rate per minute for experiment 2? So to find the time, we have to go back up and look at the time for experiment 2. The time for experiment 2 was given as this 14 minutes over there. So our change in time is going to be 14. We can simply plug that into our calculation, and then you'll have 0.023 divided by 14. And when you plug that into your calculator, you should get an answer of 1.65 times 10 to the power of -3 moles per minute. Okay, hope that makes sense to you guys there. And that's rate of reaction. It isn't too crazy. It isn't too difficult. Debello, you got the right moles for our zinc, but please remember they wanted us to find the rate of change. So you have to divide it by the time, which is awesome. But if you're answering just that part there, well done for that. Thank you so much. Thank you for everyone who's sharing the live. You guys are really awesome. And anyone who's followed more recently, you guys are great. Okay. Let's see if there's no questions, we'll go. Where did the negative go? Oh, sorry. So the negative basically, I just went straight to the final answer. So in this case here, right, the negative would be there. So let me quickly do this and show you. Let me duplicate this. And then here, I would put the negative. This would kind of go away. So my answer would be that when I contextualize my answer is that this would basically mean that's what was used up. So that is my rate of reaction. So I use up 1,65 times 10 to the negative 3 moles per minute of zinc. So the negative just means that's how much I use up over time. So your final answer should be positive when we do this particular question. Thank you for that question. Amohalang says, I can't see the formula correctly. So again, this formula isn't necessarily a formula that you're going to have on your formula sheet. You don't even get marks for that formula. That rate is equal to change in moles of a change in time, but you just need to know it from your definition, right? That rate is a change in, what's this? Rate is a change in concentration or change in amount over change in time, right? Haibo asked about the positive answer. I explained why the answer is positive. It's supposed to be positive. I just skipped that middle part of the negative. It simply means I used up 1.65, but the rate of reaction is going to be 1.65 times 10 to the negative 3 moles per minute. Okay, hope that makes sense there, guys. Someone said, why is it 1.65 instead of 1.64? I think you might have rounded off somewhere in your calculation. So you should be all right there, but there's a range, right? So there's a range. So for this particular question, remember, we all do different rounding off. So in this question, the range of answers that will be accepted is anything between 1.43 times 10 to the minus 3 up to 1.65 times 10 to the minus 3. So if you got 1.64, that's within the range. Your answer will still be marked correct. Okay, hope that makes sense. I don't see your name. I just see like a bow tie or something. But anyway, sorry. If I knew your name, I'd use it there. But thank you for that question. It's a good one there. And then Alpheus asked again 1.64 times 10 to the power of 3. Yep, they're still marked correct. If you guys got that answer as well there. Cool, guys. Let me quickly just check that I've not gotten everything there. Someone then said, if it's not in scientific notation, is it still correct? 100%, right? So if you went down and wrote 0,00165, that is still gonna be the correct answer. Just don't round it and say 0,0 and then round it off that way, right? So you gotta still keep those. It's difficult in high school, but we refer to them as significant figures. When you guys do go to varsity and you do a BSc, you learn about significant figures. And so you must keep those significant figures in there. All right. Hope that's okay. I hope I didn't miss anyone's questions. Yes.
There's a question from Alpheus and Mutlalipula and Sarah there.
Okay. Okay, let me quickly check. So Alfia says, sorry again. How did we come with 0 as the final? So at the beginning, I was saying, remember, zinc is our limiting reagent, right? So we started off with 1.5 grams of zinc. So because our limiting reagent, it's the one that's going to get used up completely. Hydrochloric acid was in excess, so we don't use all of it. So whatever that we have there, we'll start off with 1.5 grams of zinc and we'll use up all that zinc in our reaction. So which means the concentration of zinc or the number of moles of zinc at the end of my reaction should be 0. That's how I get the 0 in terms of what was used up completely. Okay. Mutlalipula says, so why do the formula of the products have a negative sign, right? I'm just trying to think about your question properly. So are you referring to the negative sign I've got here like I said, the negative shows the fact that it was used up because it's final minus initial. My final was 0. My initial was 0,023. So 0 minus anything is going to give you a negative. Okay, not anything. 0 minus a positive number is going to give you a negative number. So the negative simply shows that it was used up at the end of the day. But your final answer must be given in positive because it's simply just the rate of reaction, right? Because they didn't necessarily talk about the rate of zinc mole change. They said the rate of reaction, just that it's with respect to zinc, you're using zinc to answer that particular question. Okay. And then again, Sarah says, would I be wrong if I leave it in negative form? The answer, so I don't quite have the answer for you, right? When you go and you look at the memo and the marking guidelines especially. So the marking guidelines give a positive value when you look at the marking guidelines. That's why I'll say make it positive and say it was used up because your calculation is going to give you a negative answer there. So the marking guidelines give a positive value. And also when you think about rate of reaction, your rate of reaction usually is a positive value. It's like when you calculate work done, right? Work done by friction, you'll get a negative answer, right? But the work done is, the answer will always be positive. It's a scalar, right? You're not dealing with a vector. So you have to give it in a positive sense, where it's vectors and the negative can denote a particular direction that's useful. But at the end of the day, if it's a scalar quantity, your answer must be positive. Okay. All right. So, and then someone asks the rate formula. Oh, the rate formula, if there is a, let me just try and look. There's a formula sheet. I've got a formula sheet somewhere here. Let me just try and have a quick look. They don't give marks for it, so I don't even check the formula sheet. It's just a matter of knowing it from calculations. So yeah, because there's moles, pH, kW. There's no rate formula in the formula sheet. That's why that negative, like when they write it out in certain places, they'll put it, but the formula sheet does not have a rate of reaction formula. So that negative just, I don't know, I think they sometimes put it in the formula. If someone uses a formula, they'll put it to get rid of the negative, but you can also just use your logic to say, well, the answer must be positive. It's a scalar quantity. And whether you put the negative there, you just remove the negative. In this case, it doesn't quite matter. Okay. Hope it makes sense there. All right. And then we've got a question again. Why did the maths not go live yesterday? I did say at the beginning of the live, guys, that I apologize. We had a technical glitch yesterday, so we couldn't go live on TikTok. But we do have the recording. So that should be up to the part 1. Monday's lesson is already up on YouTube right now. You can go check it out because that wasn't live either. And then part 2 should be up hopefully tomorrow, latest Monday. It'll be up as well. So you can go check those ones out, but start with part 1 already. That will help you. It's already up. Okay. Let's quickly get back to the questions. Hey, Theo.
There's a hand up there.
Okay, Babalo's got a hand up. Babalo, you can ask your question. Please remember, it must be an academic question, right? But go for it. You can unmute and speak. Babalo, you can unmute and speak. While Pablo is trying to figure that out, there's a question in the Q&A that says, is zinc a reactant? 100%. Zinc is a reactant. Because if you look back at our reaction, there it is there. So we've got zinc and hydrochloric acid as our 2 reactants, producing zinc chloride and hydrogen gas. So yes, zinc is one of our reactants. Okay, Pablo, we'll give you 10 more seconds to try and unmute. If you can't, we're going to move on for the sake of time. Pablo, you're unmuted, but we can't hear you. Okay, I'm gonna mute you and disable talking again. And then if you've got a question, you can post it in the chat and we'll try address it. Thank you for your question there. Cool. So let's jump into the next question, right? So the next question is going to be as follows. Just get my participants up here. Okay, so the next question we're looking at is going to be question 6. So question 6 there, we get dinitrogen tetraoxide N2O4 decomposes to nitrogen dioxide NO2 in a sealed syringe of volume 2 decimeters cubed. So we see the diagram there that shows us the reaction. The mixture reaches equilibrium at 325 degrees Celsius according to the following balanced equation. So we have our dinitrogen tetraoxide, which is a colorless gas. And it can become nitrogen dioxide, which is a brown gas in color. When equilibrium is reached, it's observed that the color of the gas in the syringe is brown. State Le Chatelier's principle. I'm going to give you guys 2 seconds to quickly post that in the chat. State Le Chatelier's principle. Okay, anyone who's just joined us on TikTok, welcome. We're just answering question 6.1. Post your answers in the chat. Then once the answers are in, I'm going to do the corrections with you guys. In that case, thank you to Umpemetso for your quick fingers there. Team Zoom is waking up again, very much awake. We need Team TikTok to catch up. Okay. Someone did ask there on TikTok, which paper is this? I'll share the paper at the end of the lesson. I don't want you guys going to look at the memo and ruining the process. I want you guys to learn through it, right? When you're preparing for your exams, I need you guys to do your question paper to completion. When you're done, take the memo and mark yourself. So I'll give you guys the correct answers as we go, and then I'll tell you which paper this is as soon as we're done. Okay, but the answers are coming in there, which is fantastic. Thank you guys so much. Right, so the answer is going to be as follows. When the equilibrium in a closed system is disturbed, the system will reestablish a new equilibrium by favoring the reaction that will cancel or oppose the disturbance. Okay, I'm going to write that down. I don't like writing, but I have to do it anyway. Okay, so we've got there the definition as when the equilibrium in a closed system is disturbed, right? The system will reinstate a new equilibrium, right? By favoring the reaction that opposes the disturbance. Okay, hope that makes sense there. You can just copy it from the chat of Zoom or TikTok. People have already posted in there. So thank you guys for all the answers. You guys are awesome in this case here. Someone's asking on TikTok, do we have to state the factors in the definition, right? As the question. So in this case, no, you don't have to state the factors in the definition. You can simply say when the system is disturbed, right? That's enough for that particular case there. All right, so let's quickly look at 6.2. 6.2 says the syringe is now dipped into a beaker of ice water, while the brown color disappears. Sorry, after a while, the brown color disappears. Is the forward reaction exothermic or endothermic? Explain using LCP, the Chatelier's principle. I want you guys to post in the chat quickly what you guys think. So the syringe is dipped into an ice beaker, and then after a while, the brown color disappears. Remember, brown was the NO2, the colorless is N2O4. Is the forward reaction exothermic or endothermic? Thank you, Tibelo, there for your very quick fingers. We'll give a chance for the other ones to just put their answers in and think about it. Thank you, Cynthia, for following us. You guys are awesome. Thank you, Melon, for your answer there. Thank you, Umpameza, for your answer as well. Okay, I'll give you guys 10 more seconds. Okay, let me, in the meantime, quickly read the answers I'm getting. There's some exothermic, there's some endothermic. Okay, let's see. Most of Zoom said endothermic, most of TikTok said exothermic. So let's quickly see which team is going to win this answer, right? So the correct answer, drum roll please, is endothermic, right? Let's think about why that would be the case. So remember, we were told that after a while, the brown color disappears. So when the brown color disappears, right, we must think about what kind of reaction is that? If the brown color disappears, it means I'm going in the reverse direction, right? So my reverse reaction was favored when that happened. Now, let's think about that. So I cooled my system down. The system, by Le Chatelier's principle, says that when you cool or you bring up a disturbance, the system will favor the reaction that opposes that. So if I cool the system is going to respond to get heated again. Which reaction heats up my system? The exothermic. So we can see that the reverse reaction was favored because the reverse reaction was exothermic, meaning the forward reaction is endothermic. Okay, I'll quickly repeat that for you guys. We can see number one. So let's look at the facts. We were told that the system was dipped into ice. So that first thing tells us that we cooled our system. That is our disturbance. The response of the system is going to be to favor the reaction that'll do the opposite, that'll heat my system. That type of reaction is our exothermic reaction. So which reaction is that? The one that takes the brown color and makes it disappear, that's our reverse reaction that turns it from brown to colorless. So our reverse reaction is exothermic, meaning our forward reaction is going to be endothermic. So we can then quickly even go right here that the delta H for this reaction is greater than 0. Hope that makes sense, guys, to you guys. Then let's quickly jump on to the next question. And let's make sure I didn't miss out on any questions. I think everyone is covered in that sense. Okay, cool. Then we have there 6.3. The volume of the syringe is now decreased, right? While the temperature is kept constant. How will each of the following be affected? Choose from increases, decreases, or remains the same. 6.3.1, the number of moles of N2O4. Keep in mind, N2, the reaction looks like this. So we've got N2O4 becomes NO2. That's the reaction. So 6.3.1, I want you guys to tell me in this case here that when the volume of the syringe is decreased while keeping the temperature constant, how will the following be affected? Just say increase, decrease, or remain the same. 6.3.1, how will the number of moles of N2O4 be affected? And then quickly, just to sort of help you guys, the balanced reaction is 2NO2. That's the balanced reaction. Haibo, your answer is very Haibo. Haibo says the effect will be creases with no N or D at the beginning, just creases. That's a good one. Don't do it in your exam though. You're gonna give away a mark unnecessarily. If you write crease, you'll guaranteed to get 0. If you guess, you'll at least get a 1 out of 3 chance of getting it right. Okay. And also remains the same, it doesn't work for crease unless crease means remains the same, where increases to go up, decreases to go down, crease is to remain the same. Okay. So the answers are coming in. There's some increase, there's some decrease, there's some remain the same. The Zoom team is predominantly increase, right? So 6.3.1, the actual answer is going to be increase. If you wrote crease, you must give yourself -3 for not guessing at least the right thing, right? Let's have a look at why that would happen, right? So when we are looking at this particular reaction, if we change the volume while keeping the temperature constant, how does that affect our pressure, right, of the system? So if the volume is decreased, the pressure is increased. When our pressure is increased, right, what we want to do is favor the reaction that'll take more and create less. That's going to create less moles. So we can see here, when we look at our reaction, my product side has got more, right? Because it's got two moles of NO2. And our reactant side has got less. That's important. So when my volume gets smaller or my pressure increases, I want to have less things to occupy that space, right? So go watch the lesson on YouTube that we cover chemical equilibrium. I want to have less things in my less space at the end of the day. So I'm going to favor the reaction that creates less. And the reaction that creates less is my reverse reaction, which will increase my concentration of N2O4, which means it'll increase the number of moles of N2O4. Hope that makes sense to you guys. And then 6.3.2, I want you guys to join in there. It says, what is going to happen to the value of my equilibrium constant? What will happen to the value of my equilibrium constant? 6.3.2. I'll give you guys a minute to quickly look at that. Okay, we got a lot of answers there on Zoom. The answers are coming in on TikTok as well, and everyone is saying remain the same. Well done, right? Or as we've learned, to remain the same just means crease, right? So remain doesn't have an E. Remain the same. Sorry, guys, I'm very bad at spelling, but my numbers are decent. Okay, and the reason why it remains the same is, remember, temperature is the only factor that affects our Kc value. Very important. Well done. Haibo even mentioned it there. Okay, and then 6.3.3, what happens to the rate of the forward and reverse reactions? 6.3.3, let's quickly go do that. What happens to the rate of my forward and reverse reactions? Thank you very much, Asanda, for following. Thank you, Rotabile, for following us there on TikTok. If anyone's joined now and you're watching us and you're not following us on TikTok, please follow us. You can go to TikTok and search for the guys on Zoom at the Learning Space ZA. At the Learning Space ZA. If you're on TikTok Live and you're already there, just click that follow button. It's like right there. It's like a big red button on your right-hand side. Just click that button. Okay. Thank you, Mpile, for following us there. Okay, we're getting the answers in that case there for 6.3.3. You guys are doing really well. And the answer is going to be increase, right? So the answer will be increase, and it's going to be for both of them. Why do they both increase? They didn't ask us why, but I like to explain so that you guys understand what's happening. So the reason why they will increase is, remember what we said. The minute now our volume is decreased. So if our volume is decreased, temperature is kept the same. The result of that is that our pressure is going to increase. And remember, when you think about the factors that affect rate of reaction, pressure is one of them. If I increase my pressure, right, what happens is that my particles are closer together, my chances of having the correct orientation increases, which means I have a much better chance of having successful collisions, and then it'll increase the rate of reaction. I see there's a hand up from Tsofatso. Let me see if you can allow Tsofatso to speak there. Okay, Tsofatso, you can unmute and ask your question. Tsego, you are unmuted. We can hear your dogs in the background, but we can't hear you. Okay, Tsego, we're going to give you 5 seconds to speak. You are unmuted. We can hear everything. in your background, but we can't hear you. Okay, I'm going to mute you again, and then you can ask your question in the chat. Awesome, guys. Let's quickly continue. Theo, I didn't miss out on any questions, right?
Yes, there's nothing in it.
Okay, perfect. So then we've got the last question for question 6.4, right? Now, 6.4 is going to be as follows. 6.4 says, initially, X moles of N2O4 were placed in the syringe of volume 2 decimeters cubed. When equilibrium was reached, it was found that 20% of the N2O4 had decomposed. If the equilibrium constant Kc for the reaction is 1.6 at 325 degrees Celsius, calculate the value of X. Love these questions. I love it when they give these questions like this, right? So the first thing we need to do is somehow make sure we draw a rise table. With our rise table, let's go to our Kc equation and we can solve for the values we need to do, right? So let's first start with the rise table. I'm going to quickly just draw my table pretty quickly, right? Where we've got N2O4 decomposing, and then we got NO2. So we've got our ratio, initial, change. Sorry for my very ugly table. And the equilibrium value. Okay. So let's plug in the values that we know, right? So the mole ratio from our reaction, we know is going to be a 1 to 2 mole ratio, right? The initial values, remember, let's quickly go look at when this reaction started. We were told there that dinitrogen tetroxide decomposes to nitrogen dioxide in a sealed syringe, right? So the syringe is sealed. We started off with just our N2O4, all right? So in that case there, we started off with just that. The initial amount, we don't know what it is, but they said initially X moles of that were placed. So we're just going to have X in there. And we had none of this in the beginning, right? And then what we were told is it was found that 20% of it, right, had decomposed, right? 20% of it had decomposed, meaning that's how much was used up. Hope that makes sense. Not that it was left at equilibrium. 20% of it is what was used up. That's what was decomposed. Okay, so let's look at that. This is going to be a little bit of a tricky one, but just stick with us. So 20% of X is me writing 0.2 X, right? It's 20% of X. Now, I need to fill in the rest of the table. That's the information that was given. Let's do the rest of our table calculations. The first thing is that I need to use now my change column. I have to use mole ratios for my change column. Remember, every time you do change column, mole ratios, mole ratios, mole ratios. So the ratio there is 1:2, right? Meaning whatever I have for N2O4, I'll have double that for NO2. If you get confused, just remember with our ratio, divide with the number you have, multiply by the number you've got. So I'm going to divide by 1 times 2. Or you can do it any other way. If you can do the cross multiplication method where you've got N2O4, the ratio of that to NO2 is going to be a 1:2. And then if we've got 0.2x is to, let's call this y because we can't use x, cross multiply, y is equal to 0.4x because it's 0.2 times 2. So we know here we're going to get 0.4x. All right. So again, now the signs are important. We used up 0.2. So I'll put a negative here to say I used up 0.2 and the 0.4 is what was produced. So then I can just go to my equilibrium value simply by doing the simple maths. X minus 0.2x is going to give me 0.8x. So I'm going to get 0.8x, and then 0 plus 0.4x simply becomes 0.4x. I've got that there, and now I know I am covered. We need to go find our equilibrium concentrations. So the final thing we need to find here is going to be the concentration at equilibrium. right? So to do the concentration, remember that concentration is equal to my number of moles divided by the volume. And we were told that our volume is 2 decimeters cubed up there, right? So let's quickly go do that. So equilibrium concentration 0,8x divided by 2 becomes 0,4x, and then 0,4x divided by 2 becomes 0,2x. Those are the values I've got there. Now, those are my equilibrium concentrations. Now I can take this and put it into my my Kc equation, right? And my Kc equation is going to be Kc is equal to the concentration of my products divided by concentration of my reactants. What are my products? My products are going to be the concentration of NO2. Remember, we have to square it because in the reaction, NO2 has a 2 in front there. So we have to square that one there. Okay, divided by the concentration of my reactants. My reactants are simply going to be N2O. I need a small 4, O4. We don't square that because the coefficient of that is simply just going to be 1. And now we can substitute all the values we've got. We were told that the Kc of this reaction is 0,16, right? We need to find the value of X. So let's substitute the values we've got. Our Kc is 0,16. The concentration of our products, NO2, is 0,2x. So we're going to have 0,2x up at the top. Don't forget to square it. Concentration of my reactants, 0,4x, not squared. And then I need to go and solve for x, right? So when I'm solving for x, let's quickly try and see how we can work this number out. So 0,16 is going to remain. At the top, 0,2 times 0,2 should give you 0,04 x squared. And then we divide that by 0,4 x. Let's now multiply both sides by 0,4 x. So 0,4 times 0,16 will give me 0,064. X is equal to 0,04 x squared. And again, some of you might be asking, why didn't I just cancel out one of the x's? With a quadratic equation, don't cancel out, right? Because you could be deleting one of the actual solutions. Very, very important. Solve it quadratically, okay? In this case here, I'm going to make it now equal to 0 by saying 0,04 x squared minus 0,064 x, and then I've got a common factor that I can take out there. So let's quickly take it out. If I divide 0.04 divided by if I divide 0.064 by 0.04, I get, hold on, 1.6. So what's going to be the easiest number to multiply this out? So you can plug this into your calculators, by the way, and quickly do it. I want to just quickly try to find the easiest number to multiply across by, right? So 0.04 times 1 to... Actually, I don't even need to do that. I can literally just take an x out, and then the rest will solve itself actually quite easily. Sorry, let me just do that. Let me just take an x out, and then leave out 0,04 x minus 0,064 without factoring. And then in this case here, I know x equals 0 or, right, 0,04 x minus 0,064 equals 0. And then I can solve that where 0,04 x is equal to 0,064. If I divide by 0,04, I get 0.064 divided by 0.04. I'll get 1.6. So then that's my answer. I know it can't be 0 because a certain amount was used, right? The reaction did take place. So 0 will not be my answer. So my answer will be 1,6. And then if I write it in final terms, therefore, X equals 1.6 moles. Okay. Okay. Hope that makes sense, guys. Let me quickly go back. There's some questions that are coming up, and I'll repeat the question and the steps I took, right? And hopefully your answers are going to be answered somewhere as I go through, right? Okay. So let's quickly look at what the question said. The question said, initially X moles of our dinitrogen tetraoxide were placed in the syringe of volume 2 decimeters cubed. When equilibrium was reached, it was found that 20% of our N2O4 had decomposed. If the equilibrium constant, the Kc for this reaction is 0.16 at 3.25 degrees Celsius, calculate the value of X. So I started by doing what? Taking our rice table and then solving for the concentrations in terms of X, right? Okay, now as I go through this, so we start with our rice table. So I will draw my ratio, initial values, change in equilibrium, as well as equilibrium concentration. So the first thing that I do there is I plug in the values that were given to me. So if you look at my rice table, the values in purple is what was given to me. The values in orange is what I calculated, right? So the initial value, we were told we had X moles of N2O4. So I substituted that in. And then when we read the question initially, we were told that N2O4 decomposes. So in the syringe, they placed N2O4. There was no NO2. So I've got 0 NO2. That's where I got that from. Then we were told that 20% of the N2O4 decomposes, right? So 20% basically becomes 0.2 if you convert it into a fraction. And I put the negative to show that the change was a negative change. So I used up 0.2x. Then I did my mole ratio, right, of this to that. It's a ratio of 1:2, meaning whatever I've got of N2O4, I must have twice that of NO2. So 0.02 becomes 0.04. But that one becomes a positive. Why? Because I'm creating NO2, whereas I was taking away, or I was decomposing N2O4. Once I've got that, all it is that I plus C equals E, right? My initial plus my change equals equilibrium. So my X minus 0.2x gives me 0.8x. Also, 0 plus 0.4x gives me 0.4. That's how I got my equilibrium equilibrium number of moles. Then I need to find my concentrations, because I need to use my concentrations for my rice table, right? So to do that, I'm going to say concentration is equal to my number of moles divided by my volume. And in order to do that, my volume was 2 decimeters cubed, I think. Yes, it was there, 2 decimeters cubed. And then I divide my equilibrium moles by 2 to get my equilibrium concentrations. So 0.8 divided by 2 gives me 0.4x. And then 0.4x divided by 2 gives me 0.2x. That's how I get my now equilibrium concentrations. That's what I need to go into my rice table. Now, not my rice table, my Kc calculation, sorry. Then to do my Kc calculation, I know that Kc is equal to concentration of products divided by concentration of reactants. So my product is nitrogen dioxide. I have to square it, because when you look at your reaction, there's a 2 in the front. The coefficient becomes the power. So it's going to be the concentration of nitrogen dioxide squared divided by the concentration of dinitrogen tetraoxide, N2O4. Now that I've got that, I need to plug the values in, right? Where my N2O4, that's the value. My NO2, that's the value. So then I can plug them in. NO2 was 0.2x. Don't forget to square it. And then my N2O4 was 0.04x. And the Kc value was given as 0.16. Then I can just simply solve for x, right? So the first thing I did is I multiplied out this top one, right? You basically square that and you square that, and the bottom one remains as it is. Now, the first thing I did here is that I avoided canceling out one of my x's, because canceling out one of my x's means I'm going to get rid of one of my answers. You saw at the end, I ended up with 2 answers, right? And sometimes you'll find that the answer you canceled was the answer that was supposed to work out, right? So in this case here, I don't cancel it out, but I need to solve it quadratically. So what I did is I cross multiplied this way to get this is equal to that. Once I've got that there, I take everything to one side so that I can then factorize. In factorizing, I've got x, and then I've got this in this case here, what's happening in this case here, right? Then from there, I get my two answers where x is equal to 0, or when I solve the right-hand side, I get x is equal to 1.6. Then I said, well, I don't think x can be 0. The reason why I don't think x can be 0 is because a reaction did take place, right? And we were told that something was put in the cylinder, right? So it can't be x because, I mean, it can't be 0 because we know that we had something in the cylinder and a reaction did take place. So that's why I know it can't be 0 because something did take place. So then it must be my other value. Sometimes you'll do a question like this, and what you see is one of your answers is negative, one of your answers is positive. Then you know it can't be the negative one because I can't have a negative concentration or a negative number of moles of something. Hope that makes sense, guys. Okay, hope that made sense to you guys. That was a nice rice table question, and I think it works quite well. Okay, and I think most of the questions were answered. All right. Let me quickly go double check. Someone asked, why is 0.04 x squared on our products and not 0.04? So remember, we don't know what x is when we were busy doing this thing, right? So in our products, we had equilibrium concentration is 0.4x, but we have to first get the concentration. So that concentration goes in there, and why it's squared is because of the number up in the front that we're dealing with there. Hope that makes sense to you guys. And then any other question that we've got there, someone says, do more questions like this. If you can find a question for me to do, I definitely will do it. And then someone asked there, why can x not be 0? I did explain that we know that something was there. So it can't be 0, it can't be nothing. Okay, you explained, but it went over my head. Please do that again. But I think that was before I explained it now, right? And the signs, the rice table always beats me with the signs, right? So when I look at the signs, so the signs basically tells me what happened. Did I gain that thing or did I lose that thing? So we know that our N2O4 decomposed, right? Decomposed meaning it broke down. I lost it. We used it up. So whenever I use something up in my change, I show that with my negative. That the negative means I've got that much less. And then on the other side of my reaction, I know I gained this. So I put the pluses there, right? And that's important. You don't have to put the signs in your rice table, by the way. Most people don't put the signs. Why I put the signs is to not get confused and then do the wrong thing for equilibrium. Because for equilibrium, I must say, I must know what was used up. I must know what got gained. So you don't get marks in your rice table for putting the signs, but it's a good idea because it helps you from making mistakes next time. Okay, and then the last question was, how did you get 0.8x on the equilibrium? And it's because it's x. So think about it as 1x minus 0.2x will give you 0.8x. So 1 minus 0.2 is 0.8. That's simply how we got that. Okay, and then final question there in the chat, meaning the products cannot have negatives because it's in production. 100% Alpheus, right? So if I've got products here, then it must be a plus because I'm gaining it. But please be careful, man. I've seen a question sometimes where when you start in my reaction vessel, I start with my products. And then the first reaction that takes place is my reverse reaction. In that case, you're going to have a minus on your product side, and then you're going to have a positive on your reactant side. Just note, the question will always tell you at the very beginning. So here, initially, that many moles were placed in a syringe. So now I know where to start. And if you were told, like sometimes I'll say in an empty vessel or they'll be placed in a container, you know that the other one, there was none of it in the beginning. So just first check what you started off with. And usually the other one will be 0, but read the question clearly. I've seen trick questions where you started off with a little bit of everything. It didn't start with something with everything and the other thing with 0. There was a little bit of products and reactants from the beginning. Just read the question thoroughly. They will tell you. If they don't make mention of it, then you can assume it's 0. 90% of the time, you should be right with that. Okay. Someone there said, There's a similar one in the November 2022 paper. And here's a little hint for you guys, right? Usually, especially for physical science, the examiners like to skip years. So if it's an even number year, do even number past papers. This is now my hint for the year. If it's an even number year, so now it's 2024, do the even number papers. Do 2024, I mean, not 2024, go do 2022, 2020, etc. like that. So do the even number past papers, because usually they'll recycle questions every other year in that case there. Okay. But for practice, do lots, guys. Do lots of past papers. But those are the ones you must focus on intensely. And you can see why, yeah, this is going to be there. I took questions that were inspired by a November 2022 kind of paper, right? Because we expect those kinds of questions for this year. All right. Hope that makes sense to everyone for this question. It was a nice question that we had to go through. We are done with this one. Let's jump on to question 7, right? Question 7 is everyone's favorite section. So if you were sleepy, you better wake up. Go drink some coffee or drink Powerade or Red Bull or whatever it is. Not promoting Red Bull, but you need to be very much awake for this question, right? Because this is the one where everyone is really complaining about. Okay, so question 7 says, 7.1, sulfuric acid is a strong acid present in acid rain. It ionizes in 2 steps as follows. So we're going to have our H2SO4 plus water, giving us H3O plus HSO4 minus. That's step 1. Then step 2 is HSO4 minus plus H2O, giving us H3O plus SO4 2 minus. Then we're told to define an acid in terms of the Lowry-Bronsted theory. That's a nice and easy one. People already got it in the chat there. It's a proton donor, right? So very important there. An acid is a proton, or you can say H plus donor. Okay, nice and easy start to us there. 7.1.2, write down the formula of the conjugate base of H3O plus. I want you guys to put that in the chat, right? What is the formula of the conjugate base of H3O plus? Okay, Tebello and Neo, I've got quick fingers there. And there's Mercy and Tato and Umpile and Twilight there on TikTok. Thank you guys so much. Debuho, you're going to lose marks. You're going to lose marks. Be very careful. They said the formula of the conjugate base, right? So in formula, if you write water, you will not get the marks. The correct answer is going to be H2O, right? Which is awesome in that case there. Okay, let's have a quick look now. 7.1.3, write down the formula of the substance that acts as an ampholyte in the ionization of sulfuric acid. Right? So in the ionization of sulfuric acid, we've seen here, this is the 2-step process. Which substance acts as an ampholyte in this ionization process? Remember, an ampholyte is a substance that can act as both an acid or a base. Debo says, TikTok doesn't allow you to combine numbers and words. That is crazy. Okay, I accept your answer, Debo. Sorry for coming at you, but it was important. Some people might also not have recognized, so it was still important. But thank you for that. I recognize your answer. And then Tata writes HSO and then the words 4 minus. But other people were writing numbers there. They were writing H2O. I don't know why it was doing that to you. Okay. And the correct answer is going to be that HSO4 minus, right? The formula for the substance that acts as an ampholyte in the ionization of sulfuric acid, it's going to be HSO4 minus. Okay, well done to you guys. You're doing really well so far in this case. Okay, 7.2 says acid rain does not cause damage does not cause damage to lakes that have rocks containing limestone, calcium carbonate. Hydrolysis of calcium carbonate results in the formation of ions which neutralize the acid. Define hydrolysis of a salt. 7.2.1, define hydrolysis of a salt. Develop with the very quick fingers there, as well as Tato and Tebuho, right? Reaction of salt with water. Okay, it's a nice easy one. When you think of hydro, in hydrolysis, hydro normally refers to water, right? So hydrolysis of salt is when you react a salt with water. Okay, 7.2.2, explain with the aid of relevant hydrolysis reaction, right? How limestone can neutralize the acid. Okay, this one obviously because you guys can't write what you're writing in that case there, right? So the thing with limestone then is that we have this formation of hydroxide ions, right? And those will neutralize the excess acid because your hydroxide ions is an OH minus, and then the acid will donate an H and create water, will be there. Okay, someone says there, the reaction is the reaction of cations with water acceptable? 100%. You can also say the reaction of cations or anions with water, that will also be accepted. Thank you for that answer there. Okay, 7.2.2. So explain with relevant hydrolysis reaction how limestone can neutralize the acid, right? So what you want to see there is the following is going to happen. So you're going to have your carbonate ion, your CO3, 2 minus ion, right? Now reacting with water, right? It's going to react with water. I'm not balancing the reaction for now. I'm just going to show you the constituents of what's happening. So those two things will come together. And as they come together, right, your water is going to now act as the acid and your carbonate will basically act as the base. Right, so the water will give off an H plus to the carbonate, and then you will then have OH minus ions in that water, and then you end up with H2CO3 plus your hydroxide ions there. And I think if I to balance that, there's 2 hydrogens in this case here, and then if I put a 2 here, it should balance out my, okay, no, I'm missing one here, then we've got it that way if it's got to be balanced. So in this case here, this is what happens in that now hydrolysis reaction, right, of the limestone. And this part is really what helps to neutralize the excess acid, right? So there, the formation of my OH minus in that hydrolysis reaction basically is what neutralizes our excess acid. Okay. Hope that makes sense to you guys there. All right, let's quickly go into 7.3, right? 7.3 is going to be as follows. So 7.3 is asking us, the water in a certain lake has a pH of 5. Calculate the concentration of hydronium ions in water. I want you guys to do that quickly and post the answer in the chat as soon as you're done. Someone, let me just check the below posted there. When OH forms, there will be the neutrality of any acid left. 100%. Developer, that's very correct. Okay, thanks for your quick answers there, Mercy. Let's let everyone else get a chance to just quickly finish it off, and then we'll do the correction for that question together. Okay, let's quickly have a look at how we then do this one, right? So we're going to use our pH formula where we know that pH is equal to the negative log of the concentration of our hydronium ions, right? So to then do that, let's substitute our values in. We know that the pH was given to us as 5, negative log, the concentration of our hydronium ions will remain just the concentration of H3O plus. And then to solve for this, we know that the concentration of our hydronium ions is basically going to just be 10 to the power of minus, sorry, let me quickly do this. I forgot my equal sign. 10 to the power of minus 5. And then we must give the units as always, because they said the concentration, which is going to be moles per decimeter cubed, right? Then you guys should be fine there in that case. Hope that makes sense to you guys there. Yeah, a lot of you guys wrote there 1 times 10 to the power of 5, 100%. So if you write 1 times 10 to the power of 5 or just 10 to the power of 5, same answer at the end of the day. Someone wrote there 0,00001, 100%, same answer to Mutalepula. Well done there. All right, then we're told, here's where most people have their trouble with acids and bases, right? Then we're told the following. The following then is given. The volume of water in the lake is 4 times 10 to the 9 decimeters cubed. Lime, right, calcium oxide, is added to the water to neutralize the acid according to the following reaction. So we've got calcium oxide plus the hydronium ions giving us calcium ions plus water. If the final amount of hydronium ions is 1.26 times 10 to the power of 3 moles, calculate the mass of lime that was added to the lake. Okay, so we were basically given right now the final amount of hydronium ions. So we got given, let me just quickly highlight this here, right? That's the final amount of this. They want the mass of the lime that was added to the lake. So what they're looking for, okay, the mass of our lime, they're looking for this, given the final value that we've got there in that case. Okay, hope that makes sense, guys. And then let's quickly try and look at now how we're gonna go look at this. Before I continue, there's a question there in the chat, in the Q&A, right? It says, the concentration of H3O plus ions is 10 to the power of negative 14. So it won't be 10 to the power of negative 14. Because if you substitute it correctly, you should get 10 to the power of negative 5, not negative 14. Because if I quickly go back to this, let's imagine, you know, the steps of converting to logarithmic form. So if I go from this step here, essentially I can say negative 5, right? If I take the negative across, is equal to log of the concentration of H3O plus. And then if I convert from that to logarithmic form, in that case there, remember, the log that's standard like this is essentially log base 10. So converting this to logarithmic form, the base remains the same, 10. My answer becomes my exponent, negative 5. And then what I was taking the log of becomes the new answer, which is the concentration of H3O plus. So it's definitely 10 to the negative 5. That's how you do that. And then that should just make sense if I do it that way. Okay. Okay, Dibella, I hope that makes sense what I just said to you there. Okay, now let's come back to this question here, right? So remember, we've got the volume of water as that, and then the lime is added to the water to neutralize the acid according to the following reaction in that case there. If the final amount of hydronium ions is that, calculate the mass of lime that was added to the lake. So that's what we need to be able to work out in this case for 7.2.3, right? So in this case here, we can do a number of things for this, but what we can start by doing, right, is then we can start by calculating the number of moles of our hydronium ions, right? We can definitely do that because we were given a pH previously, right? That the water in that lake has a pH of 5. We were also given the volume of the water in that lake. So we got the concentrations. We have concentration, right? And of the H3O plus ions, we got the pH. We've also got the volume in that case there. So we can actually now go and calculate, right, the number of moles of our acid simply by using the concentration of our H3O plus in that case there. So step one, I'm going to do that. I'm going to find the concentration of my H3O plus and use that to infer the concentration of the acid in my case. So let's quickly look at that. The concentration of our that's not a 3O plus is going to be equal to the moles divided by volume. So basically what I want to do is use N is equal to C times V for that. Now let's look at that. The concentration is a concentration that we just worked out, right? Is at 10 to the power of -5. So we can then say 10 to the -5 there. The volume, we were given the volume as 4 times 10 to the 9, right? So that's the volume there of 4 times 10 to the 9. If you plug that together, you should get an answer of 4 times 10 to the 4, right? And that's going to be moles. That's how many moles now of my H3O plus, so what's basically the proxy for my acid that I've got. Now that I've got that, right, I need to now figure out how many moles of this actually reacted, right? So I need to figure out how many moles of this thing reacted. We were told that the final amount of our hydronium ions is 1.26 times 10 to the power of 3. So to find out how many moles reacted, I'm going to take the number of moles I had originally. Let me quickly really mark this. Number of moles of H3O plus originally was that 4 times 10 to the 4. I reacted 1.26 times 10 to the 3. And sorry, not I reacted that, that's what I had at the end. So I can minus that and find out what I had reacted in total. So the number of moles of H3O plus that have reacted becomes what I started off with, 4 times 10 to the 4, minus what I ended up with, 1.26 times 10 to the power of 3 moles. And then if you put that into your calculator, you should get an answer of 3,87 times 10 to the power of 4, right? So 3,87 times 10 to the power of 4. That's how many moles of my H3O plus reacted, right? So we're looking at basically this here. That's how much of that has now reacted. Now that I've got that, I can use my mole ratio, right, to work out how many moles of calcium carbonate reacted, because I can use that ratio of 2:1 to find the value of calcium oxide, that reacted, right? So in this case here, I know that, let me quickly just create space. I need another page underneath here. It's a long calculation. Okay. So I know here that the number of my mole ratio of H3O plus to calcium oxide is going to be 2:1. 2:1. And then the number of moles that I reacted, in this case, for my hydronium is 3,87 times 10 to the 4. And this is going to be X, right? So to find X, which is the number of moles of calcium oxide that reacted, I'm going to cross multiply. So basically X is going to be 3,87 times 10 to the power 4 divided by 2, because I can clearly see whatever I have of my, my hydronium, it must be double that of my calcium oxide. So calcium oxide will simply just be half, right? So then in this case here, the number of moles of my calcium oxide is going to be 3,87 divided by 2, and that should give you a value of 1,94 times 10 to the power of 4 moles. Right? 10 to the power of 4 moles. That's what I've got. But the question is not done, right? We were not asked for the amount in terms of moles. We were asked for the mass of lime that was added to the lake. So I need to go and use the mass of lime that I get there. So then to do that, I need to then just say, well, number of moles is equal to small m over big M, all right? And then substitute my values in there. So I know I've got 1.94 times 10 to the power 4 is equal to my mass is what I'm trying to solve for. My relative molecular mass for calcium oxide is going to be, I think it's 56 in that case there. And then to find my mass, I just multiply that 1.94 times 10 to the 4 by 56, which if you plug it in, you should get an answer of, give me 2 seconds to quickly just do it. Yeah, so you get 1.086. We can round it off to 1.09. 1.09 times 10 to the power of 1, 2, 3, 4, 5, 6 times 10 to the power of 6. And we have to give our answer in grams. If you want to give it in kilograms, it'll just be then 10 to the power of 3 kilograms. Hope that makes sense there to you guys. Okay, let me see if there's any questions that we might be missing out there. So we've got the number of moles reacted. That should be fine. I'm just trying to quickly go through the TikTok chat to see if I've missed anything out. 1.42 times 10 to the power of 7 grams. Tato, just double check your working out in between, right? And your calculator work. Just go back, check the values we got in between of everything else. And then you should be fine. But the final answer should be 1.09 times 10 to the power of 6 grams at the end of the day. So just double check and then, yeah, okay, you did check, you did find your mistake there. Okay, perfect. Awesome, guys. And that's basically the acids and bases question. It wasn't too bad. It's pretty okay. Let me quickly repeat the process for those that might just still be trying to figure them out, right? Someone just asked there, is it a must to write them in scientific form? No, if you wanted to write 1,086,400, you're more than welcome to write that full answer like that, grams. You will not get penalized for that. But let's just double check what's this? Sometimes they do give us those exam rules, right? That specify how your answers must be. So just double check your exam rules. If it asks you for scientific notation, how many decimal places, read the rules of your exam. Let me not act like I'm the be all and I know it all. So just check your exam rules for your particular paper. They change things every year with the exam guidelines being different. So just double check that. Okay, just to quickly repeat what our methodology for this thing was. We're told then that the volume of water in a lake is 4 times 10 to the 9 decimeters cubed. Lime, which is calcium oxide, is added to the water to neutralize the acid according to the following reaction. So we've got our lime plus our hydronium ions, which represent our acid in this case, giving us calcium ions and water. If the final amount of hydronium ions is 1.26 times 10 to the power of 3, calculate the mass of lime that was used to add to the lake. Remember before this, we were given the pH of the lake, right? So that pH of the lake, we're going to basically use to find the concentration of H3O plus ions originally. And with that concentration, we were given the volume, right? So we're going to take those factors there. We take the pH, and then we take the fact that we worked out the concentration, right, from that pH, and we were given a volume of the lake. And those three things will help us find the number of moles of H3O plus that we started off with. And there I'll simply use concentration is equal to moles over volume, converted to N is equal to CV, plug in the concentration that we worked out before, and also the volume that was given in our question, which is given over there, right? That gives us the number of moles of H3O plus originally in the lake before we neutralized it, right? But we can't now calculate anything else because what we need is now how much of it was neutralized or how much of it reacted. So to do that, we're told how much we ended up with at 1.26 times 10 to the power of 3. So I know what I started off with, that's this. I know what I ended up with, that's that. I can find what reacted in between by saying the initial value minus the final value means this is how much I reacted in between, right? Then I get my 3,87 times 10 to the power of 4. Now that I've got those moles, I can now start to use my mole ratios to find how many moles of calcium oxide. It's a 2-to-1 ratio, so I'm going to have half as much calcium oxide as I had my hydronium, right? So in this case here, I do my mole calculation, which finds that I've got half as much calcium oxide as I did have my hydronium ions in the solution, and then I get a number of moles of 1,94 times 10 to the power of 4. That's how many moles of calcium oxide or lime. The question was asking for the mass of lime. So the last step I need to do is convert my number of moles to my mass. And that's a simple one. N is equal to M over M, where my number of moles is 1,94 times 10 to the 4. We just worked it out in the previous question there. And then I've got 56 as my relative molecular mass for my calcium oxide, where our calcium will then be 50 and oxygen will then be 16. And then we end up with a mass of 1,09. Awesome, guys. I hope that makes sense to everyone. And we can move on to the next question. I'm just looking at the time. There is 5 minutes left. I'm going to try and squeeze in an electrochemistry question. If you guys will allow me, I'll maybe just post in the chat. I know the session is supposed to end at 8, but if you guys can give me 20 minutes just for that electrochemistry question, you can just post in the chat. Give me a thumbs up if you guys are happy. If you guys don't want to wait beyond 8 o'clock, it's okay. What I'll do, I can record myself doing it and I can post it up. But I'm willing to stay and do the question live. Just give me a thumbs up in the chat if you guys want me to do the question live, the electrochemistry question. Yeah, question 8 is coming up there. Tato and Tebo got a thumbs up. Okay, there's a lot of thumbs up. Okay, fantastic. Tato says even 30 minutes. Well, okay, let's do whatever we need to do. Let's do it, right? Okay, so let's quickly jump into question 8, right? Question 8 is going to be as follows. So it says, corrosion is a redox reaction that takes place in the presence of oxygen and water. Rusting is the corrosion of iron leading to the formation of iron 3 ions. Define oxidation in terms of electron transfer. Again, remember, oil rig oxidation is the loss of electrons, right? So we can just simply say here, it's the loss of electrons. Okay, simple one, I'll move straight on. Then we're told that a cleaned copper rod and a cleaned iron rod are placed in a beaker containing water at 25 degrees Celsius as shown below. So we've got iron, we've got copper in water. After a while, it was observed that the iron nail was coated with rust. The copper rod showed no visible signs of corrosion. Write down the half reaction for the iron nail, right? So in this case there, we were told already there that rusting is the corrosion of iron leading to the formation of iron 3 ions. So we need to just put the half reaction for that. So the half reaction for that to happen, we have iron as a metal, simply just Fe, right? And Fe is going to become iron 3 ions, so Fe3 plus 3 electrons. Okay. Hope that makes sense, guys. Fe3 plus 3 electrons. Please note, you can't have your double arrow in this case here. You must have the single arrow for this particular question. Okay. If you put a double arrow, you lose marks. You'll only get half. You'll get 1 out of 2 for double arrow. Okay, because it's a half reaction. 8.1.3. 8.1.3 says, does iron act as a reducing agent or oxidizing agent in the beaker? So we need to go look at our table of reduction potential, right, to see what happens. So we're dealing with iron, iron 3, and copper. So let's quickly go back to, let's go to our table of reduction potentials, table 4b. We're looking for iron 3 and copper. Let me just delete what we were doing previously. Okay, so in this case then, let's quickly go down. There's copper. I'm going to find iron 3. Iron 3 is over here, right? And the question asked, quickly go back and double check. Does iron act as a reducing or an oxidizing agent, right? So does iron act as a reducing or oxidizing agent? Let's quickly look at what's going to happen here. So our iron in these two cases here, if we look at this, right? As reducing agents go, we'll have, sorry, that wasn't going to happen. I want to just circle them, right? We have iron and our copper ions, keeping in mind that as we go up, we have increasing strength of reducing agent, right? And then on the other side, as we go down, we have an increasing strength of oxidizing agents. So on the right-hand side, right, iron is going to be our strongest reducing agent, not necessarily the oxidizing agent. Our iron ions are going to become very weak oxidizing agents. So iron, the metal, is our stronger reducing agent, which means it's going to act as the reducing agent. Let me quickly go back in there. Thank you for the answers that everyone's put in. Umpile and Debo there. Someone said they didn't hear the part about the structure of the papers being the same as 2022. Kindly elaborate a bit. So what I was saying is, when you do past papers for your physical science, put extra effort on your even number papers. So 2022, 2020, put extra effort on those papers there, right? Cool. So I hope this question made sense, that it's the reducing agent. Let's quickly go back and put that answer in. So reducing agent. Right. 8.1.4. Explain the above observation by referring to the table of standard reduction potentials, right? 8.1.4. And again, we saw right now, as we were doing it, I'm not going to go back to the table, but we saw that iron is a stronger reducing agent than copper, right? Than copper, which means in this case that iron will be oxidized. Okay, and that's basically how you'll get your marks there. You must look at the relative strengths of it and say what the reaction will be at the end. Okay, then we get given the following information. Okay. To prevent rusting of an underground iron pipe, the pipe is connected to a metal Q that corrodes easily, right? So we can see there. Then they said there, you are given two metals, zinc and copper, to use as metal Q. Which metal would be more suitable, and give a reason for your answer, right? So we want to protect our iron from the corrosion, and we have to now connect it to another metal that basically will corrode more easily. Is it zinc or copper that we can use as metal Q to prevent our iron from corroding? Let's go back to our table of reduction potentials and see how we can work that out. So we get given the options of zinc and copper as compared to our iron, right? So we already circled copper. Here's our zinc, right? Over there. Okay, now when we look at this, right, we already said copper is not as strong a reducing agent as iron is. So if we were to use copper, iron would rather be the one that gets oxidized still. But we can clearly see that zinc is way up on that table. Zinc is an even stronger reducing agent than iron, which means zinc, given the choice between zinc and iron, zinc is the one that's going to get oxidized before iron does. So in this case here, we know that zinc will be a good choice. Copper won't, right? In that case. So let's choose zinc as the metal that will be the stronger reducing agent, which will get oxidized over iron. Okay, and then they said they also, we're given a choice between the two metals and give a reason for our answer. So we can see there clearly that zinc will be the better choice. And then the reason is that zinc is a stronger reducing agent than iron. Okay, hope that makes sense, guys, for 8.1.5, right? 8.2, it says a galvanic cell is constructed using iron, an iron 3+ half cell, and a copper and copper 2+ half cell. Write down the overall, the net cell reaction that takes place when the cell is functioning, right? So when this cell is functioning, we need to now figure out the following. First of all, what are our two half reactions, right, between iron and copper? Let's quickly go back to our table 4b. So when we look at our table 4b, we've got, sorry, let's quickly remember, there was zinc and copper or iron and copper? It was iron and copper, right? Okay, so when you look at our table 4b, let's quickly look at iron and copper. So in this case here, iron is the stronger reducing agent. It'll undergo oxidation. Copper ions are the stronger oxidizing agent. They will undergo reduction. So we will oxidize iron metal. We will reduce copper ions, right? Those are our two half reactions, and then we'll need to do our net cell reaction in that case there. So our two half reactions will be written down as follows. Okay, so we've got iron becoming iron 3+ plus 3 electrons. And then the other reaction is going to be, in this case here, where copper 2+ plus 2 electrons becomes copper metal. When you do your net cell reaction, the first thing you need to do is you always have to balance your number of electrons, right? What do I mean by balance number of electrons? Make sure you've got the same number of electrons in both your half reactions. So in this case, we've got 3 in the one and 2 in the other. So I'm going to multiply this by 2 and multiply this by 3. What that does, it gives me a 2 here, a 2 here, and that becomes 6. And then it gives me a 3 here, that becomes 6. It gives me a 3 here. Now my electrons are balanced, then I write down everything else while leaving out my electrons. So clearly here we can see we'll have 2 Fe plus 3 Cu 2 plus, giving us 2 Fe 3 plus 3 Cu. Hope that makes sense to you guys. Those are the steps you must follow. Write down your two half reactions, balance the number of electrons. Once you've balanced your number of electrons, then write down your final, everything on the left plus everything on the right, leaving out your electrons. There's a few questions in the Q&A. Let me quickly go and address those. Someone asked there, are you using table 4A or 4B? I was using 4B because everyone likes table 4B. It doesn't really matter. I'm a proponent of knowing the tables well. Go watch our video on electrochemistry, right? And in there, I'll break down, why there isn't a big fuss of table 4A or table 4B. Like, just know how to use the table. But if you like, use 4B. Some learners like 4A, some learners like 4B. Use the one that you like. Your teachers normally tell you always use 4B, but they're the same table, just that they're flipped upside down. Right, okay. And then on the Zoom side, we've got questions in the Q&A that I quickly need to see. Someone there says 8.1.4, right? If I say copper is a weaker reducing agent than Fe, therefore copper won't be oxidized to that. Yeah, that's fine, right? But just try and ideally just speak about the stronger oxidizing agent or stronger reducing agent. Always say, this is the stronger one, therefore it will undergo that. Usually keep your answers that way, but you can say this other one will be the weaker one. That is also fine. Okay. Awesome. Apiwe, thank you for following us. Really appreciate it. And Rosie, thank you for sharing the live. Okay. So let's quickly go 8.2.2 and then we're wrapping up. Then you guys can go chill out, right? Okay. Calculate the cell potential of the cell under standard conditions. Hey, Theo.
Was the hand up there just now?
I think they put their hand down again. I don't see a hand up.
Yeah.
Okay. Thanks.
Yeah, they put it down.
Okay. Thanks for picking it up, Theo. And Tato says, sir, you must show us how to do the one for titanium. I always forget. I'm not sure which one you're referring to, Tato. If you can maybe write a bit more to explain which one for titanium, I'm not quite sure. Unless you think about platinum, and you're talking about where we had to use platinum as an electrode because the main thing we were oxidizing or reducing wasn't a metal. So we needed to put in a proxy electrode. So like platinum or carbon rod, something like that. Maybe that's what you're referring to. Okay. Calculate the cell potential of the cell, understand the conditions. Let's quickly do that, right? Keeping in mind our E cell is going to be equal to the reduction minus oxidation, right? Or cathode minus anode, completely up to you. Let's go for E reduction minus, there we go. E of oxidation. Okay, and in that case then, when we look at our reduction versus our oxidation, let's quickly go find our values. So in this case here, reduction, right? And oxidation, sorry, let me quickly check which cells we're using. My brain is, after 8 o'clock, it switches off almost completely. So it's the iron and copper 2 plus cell, right? Okay, so iron and the copper 2 cell, copper 2 plus, we need to go look at the following. So we've got iron there and copper 2 plus. Remember what happens to our iron? Our iron is gonna go in this direction, which is the oxidation. So that's 0.06 and negative 0.06, right? And then our reduction is our copper 2 plus 2 electrons becoming copper. So when we do that, we can quickly try and see. Oh, sorry, guys. I realize now my mistake. I've been selecting the wrong thing the whole time. It doesn't change what we've been doing, but I highlighted the wrong thing. I said highlighted the copper plus. This is the reaction that I meant to highlight initially. Apologies for that. But it doesn't change any of the answers. The answers will remain exactly as they were before, right? It's still going to be the weaker reducing agent across the board. I just highlighted the wrong thing. I really must apologize about that. But as we keep going, then we can see that now that's our oxidation is the purple one, and the reduction is going to be this one, and there's the value. So we're going to have our reduction minus oxidation, so 0.34 minus a negative 0.06. Let's quickly go put that in our answers and finalize this question. So reduction, we said, is going to be 0.34 minus a minus 0.06. And then if you put that into your calculator, that becomes plus 0.06, which becomes a very nice and even 0.40 volts. And that becomes the answer for our E cell under standard conditions. Okay. Awesome, guys. Hope that makes sense. It's 8:10. That was the galvanic cell question. And I've got one more question if you guys don't mind, right? I think the next question I've got is an electrolytic cell question. Yes, please, if you guys don't mind. I want to do this electrolytic cell question. Give me a thumbs up if you're keen for me to continue with the electrolytic cell question. And that's the last question. Hopefully by 8 o'clock we'll be done. I'll push to finish this question by 8:30. Okay, thanks for the thumbs up. Okay, let's quickly go into it. So question 9, the diagram below represents a simplified cell used for the electrolysis of concentrated chromium chloride, CrCl3. Electrodes R and T are made of carbon, right? So there we go. Someone was asking about that. But in this case anyway, we're not going to draw cell notation. Cell notation is for galvanic cells. So the net cell reaction is 2 chromium chloride becomes 2 chromium metal plus 3 chlorine. Define the term electrolysis. It's a nice and easy one. Someone can quickly go in there, right? It's the chemical process in which energy is converted, electrical energy is converted into chemical energy, right? That's going to be our electrolysis definition. Let me quickly try and put that in there. Okay, 9.1, hope that makes sense, all right? And then 9.2, we get given this graph for 9.2. 9.2 then says, the graph below, which is not drawn to scale, represents the changes in the mass of electrode T, right? Electrode T is this one on the right-hand side. And we can see that the electrode mass starts at 2,2 and it grows to some value X. Write down the half reaction that takes place at electrode T, right? So we need to find the half reaction that happens at electrode T. So when we look at this in this case here, we've got chromium, chloride, and then from the net reaction, we can see that chromium ions, which would have been chromium 3 plus, right, become chromium metal, and then chloride ions, which would have been sort of Cl minus, become chlorine gas. So the two half reactions I can take from my net reaction are going to be the following. We're going to have Cr3 plus, plus 3 electrons become Cr. And then I've got chloride. So I'm going to have Cl minus plus my electron. Sorry, Cl minus gives away the electron, becomes Cl2 plus, I need 2 electrons there. And I need 2 of these in that case there. Okay. Hope that, so those are the two half reactions, right? That makes that we're dealing with there. Then from there, we can try and look at, well, chromium gains, chlorine loses. So this is going to be reduction. This is going to be oxidation. So then the question is, write down the half reaction that takes place at electrode T. Electrode T is one that gains mass, right? So which one of these two would gain mass? Remember, chromium is a solid, right? It's a metal. So that's the only one that's going to be producing metal stuff. So we know that the reduction happens at electrode T. So we can write that half reaction here, which basically is Cr3 plus 3 electrons becomes Cr metal there. Okay, hope that makes sense there. And then if you want to make sure we've got all our, what's this? If we want to make sure we've got all our, my brain just stopped, sorry guys. If you want to make sure we've got all our phase symbols, there we go. So you know that this is going to be in aqueous solution, that's going to be solid at the end of the day. You can just add that in that case there. Okay. Let me just pause, see if there's any questions in our chat. Okay, so Tata says, I'll send you the question on inbox, the one for TI, when they say they want cell notation, 100%. And then it becomes challenging because TI is not there on table 4B. Okay, I'm with you. And then how to calculate the total charge transferred when given mass of a metal electrolytic cell? This question is going to talk about looking at charge and all of those things. Okay. So that's Aleta's question. We're going to be dealing with that one just now. So you can see there it says, a current of 2.5 amps passes through the cell for 10 hours. Calculate the total charge that flows through the cell during this time. That's for 9.2.2, right? So let's first go there and look and say charge. Well, charge is going to be Q is equal to IT, right? I don't know why in physics they write charge as a capital Q. In chemistry, they put charge as a small letter q, which baffles me every single time. But we must do what they tell us to do, so it's okay. And in that case there, our current, we're told, is 2.5 amps. And then our change in time is going to be 10 hours. But remember, in science, time is measured in seconds, right? So hours times 60 will give us minutes, times another 60 will give us seconds. Or you can just simply say 10 times 3,600, and then you'll get the same answer. So if you plug that into your calculator, 2.5 times, and then brackets times 10 times 60 times 60, you should get an answer of 90,000, or 9 times 10 to the power of 4 coulombs. That's how much charge goes through the cell at that time, right? Okay. Now they want the value of X as shown on the graph. Let's quickly go have a look at what X is. So X is the mass of the electrode, right? After 10 hours. We know how much charge flowed through the cell in that time. We want to know what the mass of the electrode is. So we're going to use this equation right here, right? Because we just worked out how much of this went through in 10 hours. If we can get the number of moles of this, we will get the number of moles of that and convert it into mass. Okay, let's quickly do that together. So in order to do that, we need to first find the number of moles of our electrons, right? So the number of moles of our electrons, do I have space? Yes, I've got lots of space. Is going to be equal, right? Or not number of moles, sorry, the number of electrons. Our number of electrons, then we use the number to calculate the number of moles. The number of electrons is going to be the total charge, right? They had it there as Q, divided by the charge of an electron, right? The total charge, we just worked it out, is 9 times 10 to the 4 coulombs. That's 9 times 10 to the 4, divided by the charge of one electron. And again, the charge of an electron is negative 1.6 times 10 to the negative 19. But in this case here, we're looking at for the number. So we'll simply just put 1.6 times 10 to the negative 19. For some reason, they omit that negative. What we need is to know the number of electrons. So divide that charge by that charge, and it'll give us the number of electrons. In this case here, it'll give us the number of electrons to be 5,63 times 10 to the power of 23 electrons. Okay, that's how many electrons. So the charge transferred divided by the charge of one electron tells me how many electrons transferred that charge. That's the first step. Now that I've got those ones there, right, I need to go and find, right, the moles of electron, and then I can find the number of moles of my chromium, if that makes sense, right? So if I can go find the number, the moles of my electrons, we can quickly do that. So the number of moles of my electrons, right, is going to be the number of electrons divided by Avogadro's number, right, Na, which is going to give us 5,63 times 10 to the 23 divided by 6,02 times 10 to the 23. In that case there, that'll give us the number of moles of our electrons. So to find the number of moles of our electrons, we'll then say 5.63 times 10 to the 23 divided by 6.02 times 10 to the 23, which gives us 0,935 moles of electrons, right? Now I can go use stoichiometry to find out how many moles of chromium, right? Because I now know how many moles of this I've got. Chromium, it's a 3-to-1 ratio, will have 3 times less, right? So my number of moles of chromium will be 3 times less. So the number of moles of my chromium is going to be number of moles of electrons divided by 3, which will give me 0,935 divided by 3. And you can plug that in there, and then you should get an answer of 0,311. That's how many moles I have of my chromium. And then the question is, we need to find out the mass of my chromium, right? Because X in this case here is the mass of the electrode, right? So this answer, by the way, is not going to be X just yet, but this is how much mass of chromium I gained. So let's first find that mass, right? Where N is equal to my mass over my relative molecular mass. Substitute our values in. Moles is 0,311. We're looking for this mass. The relative molecular mass of chromium is 52. So therefore, our mass is 0,311 times 52, which will give us 0.311 times 52, which will give us 16. What I got is my previous answer. I got 16,21, right? Oh, sorry. In that case there, And then if you keep going, so that's the mass now that we've got of, let's quickly go back, our chromium that reacted. So that's the mass, we just found this mass. Please note that isn't the mass of the electrode, right? What we just found is how much this thing went up by. That's the mass we just found, right? So that's the mass that went up, that 16,21 grams. The final mass we need to add to the original mass of our electrode, that 2.2, and then we'll get our final answer, right? So therefore, x equals 2,2 plus 16,21, and then you'll get a final answer of 18,41. Okay, there were a lot of steps in between. You might have been working with less or more decimal places, which means our decimals might be slightly different, but they'll always give us a range, right? The range of answers that they're looking for is anything between, or mine is actually even slightly off. I think I was rounding up too much in my calculation. The range is 18,32 up to 18,40. So I should have worked then maybe in like 4 decimal places or whatever before, because I kept my calculator going. So if I keep the rounding, let's see, if I go 0,311 times that 52, it gives me 16,172. So let me quickly go and do that. 172, which is weird that they would get that, because I was keeping my calculator in answer. I wasn't rounding at all, and it gave me an answer that was outside of the range, which is crazy. Okay, so 16,172, and then if I add that to 2.2, it brings me to 18,372, which that is now within the acceptable range of the answers. And I said the acceptable range is anything between 18,32 and 18,40. Those will be accepted. Okay. Yeah, so final answer of 18,172. Yeah, this one is tough because there's a lot of rounding off. So your answer can end up being quite a lot off. So maybe work with like 4 decimal places all the way down until you get an answer that's correct. So you saw, like, Tato, your answer is 18,172, right? Which is going to be below the range that we're dealing with. Also, Tato, you just added 2. You didn't add 2.2 because you initially had 16,172. You must add 2.2, which will bring it to 18,372. And that's within range. Just check your answer there. You didn't add 2.2, you just added 2. Okay, Tato, give me a thumbs up if you see the mistake you made there. And then I've got no further questions. We've got 3 minutes to 8:30. Guys, thank you so much. It's been a really awesome time engaging and having this lesson with you. I'll pause if there's any other questions you guys want me to quickly do. But until then, let's have a really awesome time together, guys. Thank you so much. I have appreciated every single one of you guys engaging. You guys made it a really awesome lesson. I really enjoy teaching you guys. Other than that, if there's no further questions, you guys can have a great rest of your evening. But I'll hang around to see if there's any questions that we might still have. Okay. So Tato says, I've sent the question in my inbox. Is this the TikTok inbox, Tato? Please let me know. So at least I know where to check. Let me see. Yes, I do see it. Okay. Okay, I see the question. All right. I think it is obviously late today. What I'll do, Tata, for you is, can I do this question as a video? And then I'll post it up on the channel. And then you guys can go watch the answers there in terms of how to do it. Cool. Awesome, guys. But I really appreciate you guys and all the questions. If there's nothing else, you guys can have an awesome rest of your night. It's been lovely